we ended last class period talking about X-rays. And so here's some pictures of X-rays. If you look at these pictures, I think the one in the textbook looks something like this, except for it has frequency written there instead of wavelength. That's where the problem is. They take the shape that looks like we have one and they put it for the other. The difference in those two is pretty clear. You have a maximum energy that can be produced. That's the energy of your photon. If the photon, or excuse me, for X-rays, it's the other way around. The kinetic energy of your X-ray, or for today's lecture, we're going to talk about, okay, so I'm saying this right, the kinetic energy of the electron, the striking the surface, if that's all converted into one photon, then you're going to have the maximum energy photon, which means the maximum frequency or the minimum wavelength. So on these two graphs, you can see that the wavelength one has a minimum wavelength, the cutoff wavelength, as you see right here. It says lambda min. And the one in frequency has a maximum frequency, F max. And so you have the same understanding, but at different positions on the graph because they're reversed. And remember, the relationship between frequency and wavelength is such that the spacing between frequencies is not the same as the spacing between wavelengths. That is, the wavelength difference going from 1 hertz to 2 hertz is not the same as the wavelength difference going from 1 million hertz to 1,000,001 hertz. So the shapes are not just reversed because the spacings change. And you can use calculus to find how that changes, but we won't. When I'm most comfortable looking at the wavelength picture because to me it looks like a whale. We have the shape of the whale here, and then we have it blowing up its little spouts. What are those things that I called it spouts? What are those really? Go ahead. What creates them? They're called the characteristic lines. Go ahead.
It's where it gets the most excited.
Well, it's where the electrons that were ionized away. If you had a core electron, one that's in like n equals 1, 2, or 3. If you have a core electron that's ionized, it gets hit by an electron, the energy is enough to kick that electron free of the atom. Then electrons fall down to that state and give you those characteristic lines. So that would cause those spikes, the line spectrum. What causes the continuous? That one's on the picture. It has the German word. What's the German word for the continuous spectrum? Bremsstrahlung. And Bremsstrahlung means breaking radiation because that Bremsstrahlung radiation is caused by the electron having an acceleration, slowing down rapidly. And so that's the source of our X-rays. What was important about talking about X-rays yesterday? Well, not yesterday, Monday and today. I may not have made it clear. X-rays are things that require that you treat them saying that light has energy HF. What nature of light corresponds with energy being HF? The particle nature. So X-rays, as well as the photoelectric effect, are things that support the particle nature and deny the wave nature of light. So today we're going to look at another one. We calculated this at the end of last class period, that 1240 nanometers times electron volt for a conversion factor. But according to Einstein, he actually, in his initial paper in 1905 on the photoelectric effect, he was specific to saying that the light that comes from an object because it's hot is caused by little electron oscillators, and these electron oscillators have specific frequencies they can oscillate, just like a wave on a string. But then later, he wrote a follow-up paper where he said, it's not just these oscillators that this applies to. All light this applies to. And so he generalized to say that all light can be treated as a particle. And so we can look at the electromagnetic spectrum and we can look at the particle energies, the energy per photon. So down here we have the frequency. If you take the frequency and multiply it by Planck's constant, you get the energy. And so we have the energy spectrum here. And so you can see that visible light is here in the ballpark of, and we can actually calculate it. What's the lowest frequency we typically use for visible light? Okay, I was going to say wavelength rather than frequency. What's the shortest wavelength we use for visible light? 400 nanometers. And what's the highest? Now, using that relationship, we can say the energies go from 1240 nanometers times electron volts over 400. Well, if you move it over, 12.4 divided by 4 is 3.1. Is that right? And the other side of the spectrum would be
1.65 through repeating.
1.6 what?
65 and then through repeating.
Okay, I'm just going to leave 1.65. So the visible spectrum is somewhere in that ballpark between 1.65 and 3.1 electron volts for the photon energy. Is that enough energy to break bonds, molecular bonds? No, it's not. Is it enough energy to cause vibrations and oscillations? Yes, it is. We worry about the radiation when it gets high enough to start breaking bonds. And it starts breaking bonds somewhere very close to here. So you get a little bit beyond that 400 nanometers, and you start having ionizing radiation that can cause you some serious problems. So with our cell phones have a frequency of, multi-mode, but 2.4 or 5 gigahertz is roughly the frequencies of our cell phones. So if we take our cell phones, let's look at the energy of, actually, let's not. We can just look here. The cell phones are in the radio range, right? They're in the gigahertz range. So gigahertz is around here. And so we can just look up here and say, well, that energy is going to be, less than 10 to the minus fifth electron volts. Do we worry about cell phone radiation breaking bonds in our DNA? No, it's really not possible. You would have to have 1 million photons all hit the same thing and be absorbed at the same time to have that happen. That doesn't necessarily mean it's perfectly safe, right? Because a microwave can kill you, right? A microwave oven, you don't put your poodle in there to dry it out. Because you are exciting vibration of the molecules, which translates into heating it. And so your microwave or your cell phone can heat tissue, but it can't directly damage the tissue. It has to heat it and then have secondary damage from the heat. So it's not like we're out of the woods that cell phones are safe, but every experiment that's ever been done shows that they are safe. One experiment that I thought was very interesting is, you have the the effect of you're told it's going to help and you think it does. You're told it's going to hurt, and it does that. The what do you call it? Yeah, placebo effect. So what they did is they took cell phones, and they attached them to people's heads for a day. And the cell phones were closed. The people didn't know if the cell phone was on or off. So that means that you don't know, you can't make your body respond, mind over matter wise. And what they found was the people with cell phones that were on had a very slightly greater amount of blood flow on the side that had the cell phone. Whereas the people that had the cell phones taped on and they were off, they did not. So they were able to measure blood flow difference based on having a cell phone next to your head. Which, any difference kind of gets you a little concerned that it might be doing something. But something else to keep in mind is the blood flow variation was much smaller than the blood flow variation if you were to stand up right now. So it wasn't like this major difference, but it did have a measurable difference. So the goal today was not to talk about cell phone safety, but it is, something that we are now getting into the realm of we can understand. Mark McLaughlin gave a nice presentation in class when he was a student about cell phone safety and why, they're non-ionizing radiation. Generally, it should be considered safe. Just thought I'd bring that up because A, we have people who go to church with him, and B, I talked about first semester his fidget cubing. Okay, let's get to our first clicker question. And we have two back-to-back, I think, here. What causes the characteristic peaks in an X-ray spectrum? Okay, we had no majority. I did very clearly state this. Talk to your neighbors and see if they got the answer. Okay, let's go ahead and answer it again. Go into backup plan. There you go. Okay, so we had the second time a clear majority. And Hannah, your card got drawn here. Give what's going on to make the characteristic peaks.
Did you say Hannah?
Hmm?
Did you say Hannah?
Yeah.
Oh, okay. So I said A because there's a when the electrons fall to lower energy states, they release energy, which causes a peak in intensity.
Okay. Now, why are they falling to lower energy states?
I don't know.
Okay, so we want to add to that. Why are the electrons falling to lower energy states?
There's some electrons that are absorbing high enough energy that they're getting kicked off, so that there's a spot in lower energy levels for those electrons.
Okay. In order for the X-rays to be performed, you have to have an electron that was a core electron, like n equals 1, 2, or 3, that had a direct collision with an electron and was kicked out of the atom. And so now you have a vacancy, and then naturally things fall to lower energy levels to give us those characteristic energies. Why could it not be, light being absorbed by electrons? That's the easiest one to say. Why could it not be that? Yeah, because it's the other way around. It's light being emitted, not absorbed. Okay, electrons slowing down. That's something that produces radiation. What do we call it? What is the radiation from the electron slowing down? The bremsstrahlung. I don't know how to spell it. I'm pretty sure it has another double letter besides the S's. It's somewhere in that ballpark. BREMSSTR. No, that was actually right.
No, you put the H
Did I put the H in the wrong place? Oh, yes. No H there. Okay. There. Briestrelung. Would you believe? Electrons speeding up. Would that produce radiation? It will, because anytime you have a charged particle accelerating, it produces radiation. But in our X-ray process, we have nothing to speed up the electrons. Hence, we're not going to have that. That would be a reverse Bremsstrahlung. Okay, next question. Which statement is true about wave theory? And we're going to have follow-up on this that says which one's true about particle theory, just in case you're curious. Three people answered, three different answers. Ready? And I don't call people's names to embarrass them. I call them because I don't want them to be sitting there thinking I answered when the computer says they didn't, because sometimes you click a button and nothing happens. Okay, now that's it's not what we're looking for now, is it? If this was on the test, this would be hurting people, right? So let's talk about this. The wave theory of light says that light is a wave. And what happens to that wave if you go from one material into another material? So it's going to go into this material that's in the red box. What happens to the wave according to the wave theory? Okay, what's the first thing that changes? The speed. That's what you said, right? Okay, so the speed is going to change. And so when the speed changes, the wavelength is what changes. So it's going to go slower when I go out of vacuum. So it's going to go like this. And we have a difference in wavelength from what we started with. So the wavelength can change for sure. So that one wasn't correct. The momentum, did we talk? We didn't talk about the momentum of a wave. When we talk about a particle, we'll talk about the momentum of a particle. We'll have an equation on it just coming up, and I mentioned it kind of tangentially before. But we didn't talk about momentum, and certainly that should have been a giveaway. What's photon mean? Particle of light. But this said wave theory. So we can cross out photon anywhere that occurs. So we've got those out of the way. So really, we only had two choices left. Now, we had to talk about that speed thing to get rid of the wavelength. But when we talked about that speed, how did we determine that the wavelength got shorter? Because we said that the frequency cannot change. The frequency can't change. I used the example of a wave on a string. When you tie two dissimilar strings together, if the frequency was different on one than the other, the knot would have to come apart. So wave theory says for a continuous wave, you can't have a change in the frequency. So these 7, which was the plurality of students, were correct. And we are going to come back to a follow-up on this about particle theory, so don't forget. 1922. The early 1900s brought lots of changes to physics. What we're studying now we call modern physics. When we started talking about relativity, we started into what we call modern physics. What's modern about it? It's the physics that was developed after 1905 when Einstein came out with his 3 big papers. So basically, Einstein's papers marks the beginning of modern physics. And, when I was a student, we were some 80-odd years away from the beginning of the modern era. You guys are a little bit farther from that. But 1922, early in this modern physics era, Arthur Hawley Compton, an American, he was studying, I believe he's American, hope I'm right. Same X-rays with a single wavelength X-ray, and he was studying the scattering of X-rays. And he found that X-rays were scattered as per the Bragg equation for scattering, but he found something really, really weird. When he looked at the wavelengths of his scattered X-rays, he found that most of the scattered X-rays had the same wavelength he had started with. Now, you're in a vacuum chamber, so the wavelength coming in and the wavelength coming out should both be the wavelength in vacuum. The speed's the same, should be the same. Why? Because the frequency can't change. It's important that we distinguish here. The previous slide said the wave theory says the wavelength can change, but not the frequency. I'm talking about wavelengths here, but it's in the same medium. So if you're in the same medium, the wavelength can't change either. So he found that we had a new wavelength appearing, a longer wavelength. And he's like, what? We can't have a change in the frequency. It's not possible if light's a wave. So in order to have a change in the frequency, what does light have to be? A particle. So the Compton effect, named after Arthur Holly Compton, is another particle nature phenomenon, something that can't be explained if light behaves as a wave. It can only be explained if light behaves as a particle. So what does Compton do? He sits down to try to calculate, okay, I have my photons hitting something. What are they likely hitting? He said, well, they're likely hitting an electron. You know, the chances of hitting an electron are much greater than anything else for this. And so he said, okay, I'm not going to go there. I want to finish this and then go to that question. If they're hitting an electron, then they're going to be potentially transferring energy to an electron. And if they transfer energy to the electron, then what happens to the energy of the scattered photon? It goes down. And that would go to a longer wavelength. So this made sense if you have the photon transferring energy to an electron. Now, as I have in a slide coming up, the classical belief was, and it still is, that scattering is caused by you have a wave coming in, and it excites an electron to oscillate at the same frequency as that wave. And so since the electrons oscillate at the same frequency as the wave, it's going to emit light with the same frequency as the wave. So no change in frequency. That's the wave explanation, and that's what produces the majority peak. The majority peak that he saw in the scatter. But the minority peak, with a shift in wavelength, that has to be something from a particle nature. So let's ask the final question now. Which statement is true about particle theory of light? Okay. 0, 9, 4, 6, 1. Who's the brave soul that said none of these? It was Aaron. Aaron is correct. None of those. Particle theory says that the energy is proportional to the frequency, and that you can have energy transferred from the photon to something else or absorbed, which would change its frequency. So you have frequency can change and the energy can change. The momentum we haven't talked about. So I can imagine people saying, well, he said that there's a momentum equation. You have momentum for a photon, so maybe that was it. I can see that as a reasonable answer. The wavelength cannot change. Well, clearly, if the frequency can change in the same medium, then the wavelength has to change. So you were left with D and E were the ones that were semi-reasonable, but it turns out that E is the correct answer. The particle theory says that basically you have BBs, and a BB would change its momentum if you made it go faster or slower. Now, the photon, you cannot make it go faster or slower per se if it's in vacuum, but by changing its energy, you also change its momentum. So the correct answer here was none of these. So that's It's an important thing to understand about the two natures, to understand the predictions about frequency, wavelength, and energy and momentum. Now let's get to Compton scattering's explanation. So Compton scattering says we have a photon that comes and hits an electron. The electron scatters, it bounces off, and the photon scatters, it bounces off. What has to be conserved during this collision? Energy and momentum. We have to conserve both of those because we have zero external force. So just like when we were talking about the collision between two billiard balls, we have to have conservation of energy and momentum. And you remember we went through all of those conservation of energy momentum equations. Well, here I'm going to shortcut it a little bit, do all the work for you, and not do any derivation. So we have the original energy of the photon, hc over lambda, or hf, right? Frequency is c over lambda, so it's the same thing, is equal to the kinetic energy transferred to the electron plus the energy that the photon has after the collision. That's conservation of energy. That gives us an equation that relates the wavelength we start with to two things: the wavelength we end with and the kinetic energy of the electron. One equation, two unknowns, you can't solve anything yet. We need another equation, so we go to conservation of momentum. Now, I can skip over this one. Conservation of momentum can be done classically, but in most cases here, we're going to be having to do it relativistically. So Arthur Hawley Compton did the relativistic calculation for conservation of momentum. And here's our equation for the momentum of a photon. You can't do any kind of conservation of momentum if you don't know what the momentum of the photon is. So momentum of a photon is the ratio of its energy to the speed of light. And we're not doing any derivation. That's just, that's a given. For relativity, we find that momentum is photon energy hf over c, or in terms of wavelength, Planck's constant divided by the wavelength. So that's the equation for the momentum. If you come back to the kinetic energy equation, we had the h over lambda. That is momentum, right? So we have momentum in both equations, and we can solve this for momentum. How did he do it? Well, there's conservation of momentum. Your initial momentum is equal to your final momentum. You start with just the photon. You'll end up with the electron moving and your photon. And for conservation of momentum, you have the x coordinate and the y coordinate. You have to have conservation in all directions. Going through the steps, ellipses here, dot, dot, dot. This is the result that Compton discovered. That the shift in wavelength, that is the final wavelength, which is a longer wavelength, a lower energy, minus the initial wavelength, is equal to h over MEC. We have a name for that. It's the Compton wavelength. Me is the mass of the electron. C is the speed of light. H is Planck's constant. Times 1 minus cosine of the angle that the photon is scattered. I'm going to go back to the picture just so you can relate the two. Back to the picture. Here. So there's theta, the angle the photon is scattered. So photon goes this direction, scatters to that. The angle between those two is theta. What's the smallest angle theta could have? 0. That would mean it just goes straight. What's the largest angle theta could have? 90 degrees would be like this. 180, it could come straight back at you. So 180 degrees is the largest angle. So theta is going to be between 0 and plus or minus 180 degrees. So if we look at this Compton scattering equation, we have 1 minus cosine theta. If theta equals 0, that means no deviation. What's the shift in wavelength? It's 0 because you have cosine of 0 is 1. 1 minus 1 turns out to be 0. So you have no shift if it goes straight through. That matches with Compton's original observation. There was no shift when it was straight forward. For your maximum deviation, if theta is equal to 180 degrees, bounces straight back. I should have finished out here. Change in wavelength equals 0 was what we found. If it bounces straight back, then what's cosine of 180 degrees? Minus 1. And to be clear, what's cosine of minus 180 degrees? Also negative 1. 1 minus a negative 1 is 2. And so you have delta lambda is equal to 2 times h over mass of electron c. Why does it have the mass of an electron in there? Why do you think it has the mass of an electron? That's the thing that it bounced off of. It's the mass of the thing it bounced off of. Right? It didn't come in through any magic, we randomly pull in something. The thing it bounced off of had mass me, so its momentum would be mev. That's where it comes from. I already did the calculation here. I said we call this here the Compton wavelength. And if we put in our numbers, we see that it's really small. 2.426 times 10 to the minus 3 nanometers. That's 2.426 picometers. You have to have really sensitive equipment to measure that small of a wavelength. Well, what would happen if instead of bouncing off of an electron, it bounced off of a proton? Like you have hydrogen gas, and instead of having a photon bounce off an electron, bounce off of a proton. How would this equation change? Yeah, the bond would be bigger because you'd put in the mass of a proton, which is what, about 800? No, it's more than that. 1,800 times bigger? And so what's that going to do to the wavelength if you have Compton scattering off of protons? It's going to be smaller by like 3 orders of magnitude. It has actually been measured, but it takes really precise measurement. So we generally just worry about the electrons because those are the least massive things for them to scatter off of. So you can have Compton scattering off of any size object, but the more massive it is, the less observable the scattering is. So what's the whole point of Compton scattering? Yeah, the point is that only a particle nature of light can explain it. A wave nature of light can't explain it. So you need to understand what it is, but even more important than that, you need to understand what's significant about it. So just a little problem to keep us from, talk and no examples. An X-ray photon of wavelength 10 picometers is scattered through 110.0 degrees by an electron. So we don't have to worry about, could have been a proton, we don't know. What's the kinetic energy of the recoiling electron? How would you calculate that? Give me a process.
Figure out the change for the proton state throughout the change for the electron.
Okay, photon, not proton, but yes. We use the Compton scattering equation to calculate what the difference in wavelength is, so we get the new wavelength of the scattered photon, and then we calculate how much energy the original photon had, how much energy the final photon has. The difference in those is how much kinetic energy transferred to the electron. And so let's go through that. We have wavelength prime minus wavelength is equal to the Compton wavelength times 1 minus cosine theta. Notice I put the Compton wavelength because, hey, let's keep it simpler. That Compton wavelength was 2.426 picometers. and I put in the 10.0 picometers for my initial wavelength. So that means that I put a 1 down on bottom instead of on top. I meant to do it like that. What's my new wavelength going to be?
So it's 10 picometers plus Compton wavelength times 1.342 is what you got.
Mhm. So what's 1.342 times 2.426?
That's 3.25 or 3.26 times 10 to the minus 12.
How many significant digits do I have in this number? 3. I wrote 4, so I'm not throwing away much information, but I have only 3. So now that I have that, my energy initial was hc over lambda. The energy final, these are for the photons, hc over lambda prime. Kinetic energy of the electron is equal to equals, and now we just got to do calculation. Well, times 1 over it's what? 4 point what?
4.879 times 10 to the negative 27.
And what would those units be? Now, somehow that doesn't seem right, because it should be somewhere in the ballpark of, yeah, it should be a bigger number, I think.
I got on that.
4.88 times 10 to the negative 15.
Is that what you got as well?
I got times, same number times 10 to the negative 20.
Well, everybody agrees it's 4.879. It's going to be somewhere close to the minus 20. Because
Oh, that's why.
minus 34 and 3 makes minus 31.
Oh, I'm wrong because I didn't convert to meters. I was still in picometers.
Divide by, or add 12 to 30 minus 31 is minus 19. And I think that the 20 was probably the right number.
What is the 2.9
Times 10 to the what?
Out there you have it 10 to the 30. Is it kind of the issue?
Where are you talking about? Oh, yeah, yes. Oh my goodness. That's a horrible mistake. Yeah, that makes a difference. Yeah. Which means that probably the 15 was more accurate, huh?
I got negative.
It's negative 15.
Yeah.
Yeah, it's like
Yeah. My that difference of 5 made the difference to 15. It's good to have people check. That's in joules. What would the more common unit be that we would use for something like this? Electron volts. So how do we convert that to electron volts? You just divide by the charge of an electron.
Uh, 30,383.9.
Now, I wrote ridiculous significant digits here. The correct answers would be 4.88 times 10 to the minus 15 joules equals 30.4 kiloelectron volts. Right, we took all those digits, but in the end, we should report it with only the ones that are meaningful, not extra digits that don't mean anything. Okay, so a lot more work than you would expect for, a small little 2-sentence problem, but it's not difficult in work, except for when I wrote the wrong speed of light. It's putting the ideas together and executing. Okay, this is our last clicker question. Which phenomena, I think it's our last, support a particle theory for light? Not only do I think it is, I also believe this is the last slide I prepared for today. That makes 2 days in a row. I better prepare more stuff. Oh yes, and this one here, you answer all that are correct and hit enter. All right, we have everybody in, and the answers are 18, 3, 14, 2, 10. All right, now we analyze them. So we ask this person to choose one and give a reason why. And this person is Gila. Choose one that is in support of particle theory and your reason why.
I picked one of my answers was A.
One of them was A, okay.
Because we were just talking about it.
Because we were just talking about it. What was the method, the mathematical method that he used to solve, to explain the Compton scattering?
The wave.
The what?
The wave. The bird.
No, that was for, it's on here. That was the X-ray production. He used conservation of energy and conservation of mass using the energy of, or not mass, of momentum, using the energy and momentum equations that you get from particle theory. So he used particle theory to explain it, and the actual observation matched the results he got from that. So that was a correct answer. And let's go to another student now. This one is Megan Bush.
X-ray production, because the equation is E equals HF.
Okay, X-ray production, because once again, you use E equals HF. That's a really good identifier. If we use E equals HF, it had to be particle theory because that doesn't appear in wave theory. Okay, and there is one more correct answer, which is probably clear. Gabrielle.
So the other right one would be the photoelectric effect. Partially because we spent a couple hours yesterday. Demonstration of particle effects. I remember one of the ones from yesterday was that in testing the photoelectric effect, you could calculate an accurate Planck's constant, which you could only do if it was partially with nature.
Right. Okay, so those were the correct answers. Rayleigh scattering. I'm guessing a lot of people don't even remember talking about Rayleigh scattering. Rayleigh scattering is what makes the sky blue. Remember we talked about why the sky is blue? And that's caused by what I said when I talked about the wave theory's idea of what causes scattering. We have light coming from the sun. It's absorbed. Well, it's not absorbed. It makes an electron oscillate, and the energy then goes into the electron oscillating, and then the electron radiates energy in a direction perpendicular to the direction it's oscillating. And that gives us a polarized, scattered light. But it all had to do with it being a wave. So Rayleigh scattering is a wave nature idea. The diffraction, well, we did diffraction experiment, right? We did diffraction and polarization at the same time, same lab. That's because diffraction and polarization were both wave nature phenomena. Polarization, having a wave that's oscillating in one direction, doesn't make any sense if you're talking about a ball traveling. Right? So polarization has to be a wave nature phenomenon. The diffraction was you had the light going through two slits and then interfering. If it's a particle, the particle can't go through both slits at the same time. It's got to go through one or the other. Can't interfere with itself. It's just going to, I mean, sure, it could hit and bounce off, but you can't have regions where two particles come and add up to zero particles. Right? That doesn't work with the particle nature. It only works with the wave nature. So we can take this and we can divide up the things that we studied recently under the headings of particle and wave. And for particle, we had X-rays and photoelectric effect. Which were just the reverse of each other. And Compton scattering. There's one more, pair production, where you have photons disappear and produce two particles, right? That doesn't work with a wave. You're creating matter from light. For the wave, we had anything that has to do with interference. And so the example we had there was Young's double slit. We could also do the thin film interference. That's also a wave-only phenomenon. Rayleigh scattering. Polarization. Now, what is obviously not listed under these that we studied for optical properties? Okay, reflection and refraction were what I was looking for. You guys hit them both at the same time. These can be explained by either a wave nature or a particle nature. The Newton's explanation for refraction was incorrect. He said that things went faster when they go into glass as compared to in vacuum, but those are things that could go with either one. So this whole duality is what we end up with. As we understand light, it has two natures. And so you might think of, okay, what's something that we commonly deal with that has multiple natures? As soon as I look for practical examples, my mind goes blank. But I'll go to the classic one day. The four blind men come and encounter an elephant. And one of them feels the tail and says, oh, it's like a snake. And one of them feels the leg and says, it's like a tree. And one of them feels its side, and it's like a wall. And one of them feels the trunk, and I can't remember what he says. Okay, so I'm bad at that one. We have the same thing with light. Light has to have just one nature, really. And we see a different manifestation depending on how we're observing it. And so, at least to me, what this indicates is we still have a lot to understand about light. We think we understand so much, but there's got to be something more fundamental to help us understand what's really going on, instead of just saying, well, it has two distinct natures, and in any experiment, you'll see one or the other. And that's what I'll outline today.